This upcoming screen recording shows a way to address the common challenge of drawing a board that touches two discrete points in space. This is simple enough when both points touch the same side of a board, but when these points touch the board on opposite sides, this scenario becomes challenging. Two common examples of an application for this would be a Z-brace on a rustic door or a wood rafter that sits on a top plate and reaches a known ridge height. This was a challenging operation in the days of hand drafting. Back then it relied on the use of a compass, a ruler, and a rudimentary knowledge of what mathematicians call Thales' theorem. All most of us knew was it allowed us to position two parallel sides of a board accurately in space the first time and without guesswork. It is true that one can simply draft these lines in Revit to recreate the hand-drawn solution. But if one is working in the family environment, it becomes necessary to have a deeper understanding that permits the relationship to flex in this parametric environment. Like many things in Revit, a little trigonometry can help your ability to take full advantage of the program without giving up on the use of geometry that is non-rectangular. In the upcoming footage, I'll show how the use of the appropriate diagonal should allow you to use arcsin functionality to expand your understanding of this problem into parametric functionality. Judging by what I've seen emerging in the contemporary built environment, it is my sense Revit encourages a strong use of rectangles. Without mastering some trig, it is easy for a Revit user to become highly constrained by this, and it is the simple goal of this video to help users to literally work outside the constraints of a box. I hope you find it helpful. All right, I'm going to do a screen recording of the making of a simple Z-braced door panel. There's some trigonometry involved. I may take the time to have a supplemental video describing some of the subtler parts of this as we move forward, but let me just start by doing it, and we'll take it as it comes. All right, we'll start just by putting in a few reference planes. Very typical procedure. We'll put a reference plane there and a reference plane there. While I'm doing the reference planes, I'll put in the stiles and rails, and for the purpose of this family, I'll make the stiles and rails the same width. We'll have that be the overall height and that be the overall width. I will call this a width and simply just call it W for now, and call this H. Go there and call this H. And then we might as well just put the same, just for the sake of this illustration, I'm going to have all of these dimensions be the same. So instead of calling these stiles and rails, I'm just going to call them surround. Okay, and then we'll do the diagonal brace. Goes from here to here. And sometimes I'll isolate reference lines and reference planes just so I get the proper snapping behavior, but I don't think I'm going to be required to do that here. All right, and then we want to get the this diagonal length. So to do that, we're going to need to create an inner width and an inner H. And for the purpose of this this video, to keep things short, I'm going to use acronyms here. So I'll just say IH and say IW. And IH is going to equal H minus 2 times surround. And I'll just copy this because I'm going to use it on the other variable as well. And then here we'll say width, the inner width is going to be width minus 2 times surround. Oh, we got a double minus there. That's not cool. We'll do that. Okay. And then we want to create the diagonal for this. So just I'll call that D for diagonal. And we're going to want to use the Pythagorean theorem here. So we're going to say square root, open parentheses, and we will say IH squared plus IW squared. And we'll hit return. Oh my goodness, that worked the first time. We got lucky. Okay, so Okay, so we have that much now. Now we should have this dimension already calculated. Now to get what we're trying to do, and I'll just kind of quickly just draw this before we do it, but what I'm trying to do is do a Z-bar that basically, a Z-brace that comes here and comes here, comes down here, and basically forms a parallelogram where opposing sides of a board are intersecting the corner condition. And this just geometrically, trigonometrically, however you want to think about it, it's not something that is, you know, at first blush when you're using Revit is easy to do. And I just want to show here how a little bit of trigonometry can go a long way with Revit, expanding its functionality. So what I'm basically going to do is just to reinstitute that for a second. We've got, what we essentially have here is a triangle, and you can see that little dashed line that just came up there. That's not actually the dashed line we want to look at. Dashed line we're interested in is the perpendicular condition where we come here, where it's just perpendicular there. So this diagonal that we calculated a minute ago now becomes the hypotenuse of a long right triangle, where the this angle is opposing this side here, and this is what in trigonometry they call the opposite angle, or the opposite side. You may recall from trigonometry that a sine is opposite over hypotenuse, and that would mean that the arcsin, if we want to get the angle here of this triangle, the arcsin is going to be opposite over hypotenuse arcsin. So Revit is perfectly capable of doing arcsin. So we do need to say now what we want our board width to be. So we will just say board width. I'm going to use BW for board width, and for now we'll make that a 5.5 inches. Just make it a 2x6, I guess. I'm not sure if that's to scale with the drawing. I'm hoping it is. And now what we want to do is get this deviation angle that I was just talking about. So this angle off of this pure diagonal over to the parallel sides of this board that is running in this Z formation here. So what I'm going to do now is call out a deviation angle, and I'll just call it a deviation angle. I'll spell this one out because it's so critical to the substance of this video. So the deviation angle is going to be the arcsin. I think we just use arcsin, and then we will say board width divided by the diagonal, which is D. So just take that, hit return. Okay, now I'm encountering an issue here. Why am I encountering an issue? Arcsin, BW, board width divided by D, and I wonder if it's, oh, because I'm misspelling this. All right, let's see if that works. There we go, 6.60. So now what I'm going to do now is get rid of this little, these symbol lines here, and now we're going to create a reference line in this lower corner. And if you're having trouble getting the snapping to work with this reference line, which is not an uncommon issue with Revit, just do this, and you can always isolate the line and its reference lines if you need to, but that seemed to work okay. We're going to see if it works, but first I'm going to draw this same angle over here. I'm going to snap this to this upper corner. That snaps. Whoops, I got a little repetition here. Oh, I think it's maybe snapping to that. That is an extra line that we do not need there. So I'm just going to take that and snap that. It's still giving me grief. I'm hoping that it's behaving itself, and we're going to find out here in a second. First, I'm going to just add a few dimensions here to just constrain this. So we'll put that there. We'll take this one, we'll take that angle here, and we want both of these angles to be the deviation angle. So I'm going to go here and say deviation angle, and that's a good sign. They're parallel. I guess the other thing I'm going to do here, just to check to see if this is in fact a 5.5 inch wide board, is to run this across, and you can see it is, so we're on the right track. Now we probably want to check to make sure that all of our snapping is correctly anchored. All of our reference lines are correctly anchored. So I'm just going to change the size of this door here a little bit, make it 5 feet by 4 feet wide, and maybe at the same time ambitiously ask the surround to be reduced to 3 inches, And we'll just try all of those changes at once. A lot of times it makes sense to only change one thing at a time so you're able to understand what is going wrong and what's not. But this seems to be working well. I'm going to do this just to change the scale, just to reduce the text size here. And then, of course, now if you want to, this is the point at which you can either create separate extrudes if you're working with different material textures and want them to go in different directions, or if for the purpose of this video we want to just show it all as one object. I'm going to try ambitiously to do all of this at once here. And I'm just going to snap that and snap that and snap this and snap this. And I should have had the lock button clicked down there. My bad. But I'm just going to go here and go here and get that to close and get that to close. Get this to close. Get this to close. Unjoin elements. Okay, and it's usually the case that when I do this, it actually requires a couple times flexing it and just checking what everything is anchored to. So I make no promises here, but let's just look at it as a 3D view here for a second. Okay, and I haven't specified the depth of this yet, so it's just kind of whatever it is. But I'm just going to try making this board width a little narrower, 3 inches, and maybe we'll make the surround a little wider, 5 inches, and then we'll make this maybe 6 feet wide, and this height 6 feet wide, so it's like a square, and see how that looks. Okay, well, there you go. So anyhow, if anybody is curious how you can make a Z-braced barn door, this same approach works with doing trusses and rafters. And if I do a little animation, maybe that'll become evident in that accompanying document. All right, thanks for watching.